Okay, so this is Chapter 3, Lesson 3, and this is the last lesson in this unit. And today we're going to talk about empirical and molecular formulas, and we're going to talk about limiting reactants. Now, we did empirical and molecular formulas in reagents chemistry, so this should be a little bit of a review. We're just going to add the skill level that we are doing this year. So the first thing that we want to talk about is how do we calculate the molecular formula? What do we need? So in order to calculate the molecular formula, we need two things. We need the empirical formula. I'm just going to abbreviate that EF, but please make sure that you know that I'm talking about the empirical formula. And we also need the molecular weight or the molar mass. Of the molecular formula. So I'm going to abbreviate that MF. So we either need the molecular weight or the molar mass, and we need the empirical formula. If we have those two things, then we can calculate the molecular formula. And in order to do that, we have to figure out what the whole number multiple is. So the whole number multiple. And remember, your molecular formula is just that. It is a multiple of the empirical formula. So to figure out what that multiple is, we take the molecular mass and we divide it by the empirical formula mass. And that's going to give us a whole number. And then we simply take our empirical formula and we multiply it by the whole number. And that's it. So let's get started. Let's do some practice. So in this problem, they want us to calculate the empirical and the molecular formula. So the first thing we need to calculate empirical formula. We've been doing that. And then we're going to calculate the molecular formula. And we are given the molar mass. So we're talking about ibuprofen, a headache remedy, contains 75.69% carbon. So we know that 75.69% is really the same as 75.69 grams of carbon. And we've got 8.80 grams of hydrogen. And we have 15.51 grams of O. So first thing we need to do is get these into our moles. And honestly, by this point, you should really be pausing me, and you should be trying to calculate the empirical formula on your own and then double checking it against mine. This way you're increasing your skill level. And we see that oxygen has the smallest number of moles. And when we do that, we get 6.5 here, and we get 9 here, and we get 1. So the problem with that is the 6.5. So I'm going to have to multiply everything by 2. So 6.5 times 2 is going to be 13 carbons. 9 times 2 is going to be 18 H's, and 1 times 2 is going to be 2 oxygens. So this is my empirical formula, C13H18O2. Now, to get my whole number multiple, I need to take my molar mass, which was 206, and divide it by my empirical formula mass. And actually, when I do the math on this, I come out to 206. So this equals approximately 206. So in this case, the empirical formula and the molecular formula are the same. Okay, let's try another one. Nicotine, a component of tobacco, is composed of CH and N. A 5.25 milligram sample of nicotine was combusted, producing 14.242 milligrams of carbon dioxide and 4.0830 milligrams of water. What is the empirical formula if nicotine has a molar mass of 160 plus or minus 5 grams? What is the molecular formula? So again, we need to calculate the empirical formula. We need to calculate the molecular formula, and we are given a molar mass of 160 grams per mole plus or minus 5 grams. All right. So this one's a little bit harder because I wasn't given the straight up elements. So I'm back to my stoichiometry. I have to do a couple of things. So let's talk about what we have to do. First of all, I notice I'm in milligrams. I have to decide if I'm going to work in milligrams or grams. That's up to you. I like working in grams. I know that I can extract my carbon from my carbon dioxide, my water. I'll get my hydrogen, and I still need nitrogen. So I'm going to have to get those grams, go back and subtract it from my whole sample of 5.250 and get my nitrogen. So I've got a little bit of work here to do. So let's start with carbon, and I've got 0.014242 grams of CO2, and that's 44.0095 grams of CO2, and that's 1 mole. And then I know 1 mole of CO2 has 1 mole of carbon. I need to write smaller here, or I'm not going to fit everything. I'm going to cram this in because I got to change it back to grams because I need the grams of carbon. So I'm going to do 1, 1. I'm just going to do 1 CO2, 1 carbon, and this is a mole. And then 1 carbon is 12.011 grams. Okay, sorry about that. So that's going to give me 0.0039 grams of carbon. Okay, so now let's do hydrogen. So this was carbon, this is hydrogen. I'm extracting that from the water. So I've got 0.004083 grams of H2O, and that's 18.01528 grams of H2O, 1 mole H2O, and in 1 H2O I've got 2 H's, and 1 H is 1.00794 grams. So everything cancels, and I am going to be left with grams of H, and my grams of H are going to be 4.569 times 10 to the minus 4 grams of H. So I'm not going to write this down, but just to save space here. But now you have to take your sample, right? So our sample is going to be in grams, 0.005250 grams. This is our sample. And we're going to subtract from that our grams of carbon and our grams of hydrogen. And that's going to give me my grams of nitrogen. And my nitrogen grams are going to be 8.93 times 10 to the minus 4th grams. So now I have my grams. Now I have to change my nitrogen to moles. So we know that 1 mole of N has a mass of 14.0067 grams. And that's going to give me 6.376, different color, 6.376 times 10 to the minus 5 moles of N. Okay, now what I'm going to do is I'm going to go back and figure out my moles. So I am going to do this. My 0.014242 divided by 44.0095 times 1 divided by 1, that's going to give me my moles of C. Over here for H, I'm going to go all the way to the 2. Okay? This is going to give me my moles of H. Remember, I already have moles of nitrogen. So when I calculate that, I am going to get 3.236 3.236 times 10 to the minus 4th moles of carbon. And then for my hydrogen, I'm going to get very close to that, 4.533 times 10 to the minus 4th moles of H. So now it's a matter of dividing through by the smallest. You can see that nitrogen is the smallest. So I'm going to divide everything by 6.376 times 10 to the minus 5. So for nitrogen, I get 1. For hydrogen, I get 7. And for carbon, I am going to get 5. So C5H7N. That equals my empirical formula. Now, remember what the next step is. I'm looking for the molecular formula. So I need to get the empirical mass of this, which I'm going to tell you is approximately 81 grams per mole. Then I'm going to take 160, divide it by that, and I get 2. So my molecular formula is twice that of my empirical formula. So my molecular formula is going to be C10, H14, N2. And that is my final answer. A lot of work, but not difficult work. You just have to remember the steps. All right. Let's move on. So now we're going to start getting into more of the stoichiometry. And we've been doing stoichiometry all along, but now we're going to utilize the molar relationships a little bit more. So if I start with grams of compound A, I can use the molar mass of A to calculate the moles of A, and I can use the molar ratios from the balanced equation in order to figure out the grams of a separate compound. So I know that sounds like a lot, but it's basically going to be very structured. You take your moles of one thing, you change it to grams. You use your molar relationships, your coefficients in your balanced equation to then calculate the moles of something else and use stoichiometry to figure out the grams, turning that into grams. So let me demonstrate. We're going to start off really easy. Given the reaction for the formation of B2H6 diborane, how many grams of diborane can be prepared from 3 grams of lithium hydride? Well, the first thing that we need to do, always, number 1, balance the equation. That's the first thing. Second, use the grams given and stoichiometry to determine grams of X, whatever it is you're finding. So I've got LiH plus BF3 yields Li BF4 plus B2H6. So when I balance the equation, let's see. I see a problem right away as I glance through this. I'm going to have a problem with F and F because F's only in one place, B is in 2 places, but I got 3 and 4, so that's an uneven number. So you might think that the least common multiple will be 12 on this, but the problem is that B is in 2 places. H is only in 1 place, so it might be better to start with H. So I've got 6 H's here. I'm going to put 6 here. That's going to give me 6 LIs. That's going to really turn up my F's to 24, which means that this has got to be 8. And I've got 6 B's here and another 2 B's here, so I'm balanced right now. All right, balance the equation. Use grams given and stoichiometry to determine grams of X. So they gave us 3 grams of LiH, 3.0 grams of LiH. So let's get that from grams into moles. 1 mole of LiH is going to have a mass of 7.949 grams. So my grams cancel. Now I'm only at moles of LiH. I want B2H6. So what's my molar relationship between LiH and B2H6? It is 6:1. So I have 6 moles of LiH and I have 1 mole of B2H6. Right here, you saw how I used the molar relationships of the balanced equation. And now I'm going to do is change my moles back to grams. 1 mole of B2H6 has a GFM of 27.6694. So this cancels, this cancels, this cancels, this cancels, and that canceled. Now it's just straight up math. 3 times 27.6694 divided by 7.949 times 6, and I get a grand total of 1.7 grams of B2H6. And that's my answer. The one thing that's really important about doing molar relations in stoichiometry is if they only give you one reactant, like here they only gave us the LiH, then you can assume that the second reactant is in excess, meaning you have plenty to run the whole reaction. We're going to see at the end of the PowerPoint, however, when they give us grams of both reactants, and you have to determine what the limiting reactant is. In this one, it says, given the reaction, you're using the same one, how many grams of BF3 can be prepared from the LiH? Well, I don't know that I'd like this question, can be prepared. I probably would say is needed, okay, in this reaction. But regardless, they want us to figure out the BF3. So, again, I'm just going to start from the beginning because I don't know the moles of LiH, so I'm just going to rewrite it. So now I've got 3 grams of LiH and 1 mole of LiH, which is 7.949 grams. And now I'm going to BF3. So I've got 6 moles of LiH, and I'm going to 8 moles of BF3. And now we need grams. And we know that 1 mole of BF3 has a GFM of 67.8062. So moles cancel and grams of LiH cancel. And now we just run the math, and I get 34.12 grams of BF3. And that's my answer. Okay, moving on. A common laboratory method for preparing O2 involves the decomposition of KClO3. How many grams of oxygen is produced from 4.5 grams of KClO3? First thing I need to do is what? Balance my equation. So my oxygens, 3, 2. I know this has got to be least common of 6. So this is going to be 2, 3, and then this is going to be 2. And now I'm balanced. I'm starting with 4.5 grams of KClO3. Sometimes it's just helpful, and this is your comfort level, to circle what it is you're looking for to keep you focused. So you want oxygen. Okay, you can always do this. And we know that 1 mole of KClO3 has a GFM of 122.5495. And in our balanced equation, we have 2 KClO3, and I'm going to 3O2. Wow. Sorry about that. And 1O2 has a mass of 15 point, nope, I gotta double it, sorry. (31.9988). Because it was O2, and that's grams. So this cancels, this cancels, this cancels, this cancels. And when we do the math, I get 1.76 grams of O2. All right, let's go to the next problem. Propane is a common fuel used for cooking and home heating. What mass of oxygen is consumed in the combustion of 1 gram of propane? Well, this question assumes that you know what a combustion reaction is. It also assumes that you can write the formula for propane. Recall from Regents Chem, prop means 3. So it's got 3 carbons. It's an alkane. So the general formula is CnH2n plus 2. Or you could always draw it out. And then you knew that all of these would have to be H's. So C3H8. And we need oxygen, and all combustion reactions produce CO2 and H2O. So we have to balance this. So 3 C's, 8 H's. So that's 8 H's, 4 times 2. Got 4 O's here, 3 times 2, 6 O's there. That means I need 10 O2 right here. So that's going to be a 5. 5 times 2 is 10. That's great. I'm balanced. All right, I'm starting with 1 gram of propane. I'm just going to put a P for propane because that formula is going to take up too much space. And we know that 1 mole of propane has a mass of 44.09652. And in our balanced equation, we have 1 propane and we have 5 oxygens. And we just said that the mass of 1 O2 is 31.9988. O2 cancels, propane cancels, grams cancel. I do the math, and I get 3.64 grams of O2. Okay. So I'm actually going to save the detonation of nitroglycerin for class Tuesday morning, just because this is more of a higher level problem. So there's a couple of things going on here, and there's a couple of ways to figure it out. So we're going to talk about that one in class. So these last 3 slides you don't have. I'm adding them, and you can just write down what a limiting reagent is. You don't have to. It sounds exactly what it sounds like. Sometimes after one reagent is completely consumed in the reaction, some of another reagent is left over. The reagent which is completely consumed limits the extent of the reaction. Therefore, it's called the limiting reagent. The one that's left over is called the excess reagent. So here you can see I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 keys. I have 5 locks. Therefore, the limiting reagent is the locks, because the object is to put a key in every lock. Hopefully that explains limiting reagents. So I'm going to do 2 examples. If you want, you can write these on the back of your PowerPoint, and you can just write the reaction. So I'm giving you a balanced reaction of 6 LiH plus 8 BF3. We already worked with this reaction. The diborane, 6 LiBF4 plus B2H6. Okay, so I'm going to write down what they gave us. They gave us 5 grams of LiH, lithium hydride, and 5 grams of boron trifluoride. And they want to know how much of which reagent would be left over. So they want to know, okay, the excess reagent. That's what we're trying to find out. We know the quantities that we're starting with. We can certainly calculate the moles because we have the molar mass. And we have to look at the molar ratios. So before we can find out how much of which reagent is left over at the end, we have to find out what the limiting reagent is. So this is how I'm going to do that. 5 grams of LiH. And we know that 1 mole of LiH has a mass of 7.9 grams. And we have 5 grams of BF3 and 1 mole of BF3 has a mass of 67.8 grams. So I'm going to calculate my moles. And what I'm left with is 0.633 and 0.075. However, in order to determine the limiting reagent, I have to look at the ratio at which they combine, 6 to 8. So I need 6 moles of this, 8 moles of this. This is going to give me 0.105, and this is going to give me 0.009. So you can see that the BF3 is going to be the limiting reagent because it is the one that is going to get used up the quickest. So I'm going to use all of my BF3. So what I'm going to do is I'm going to then go back. I'm not going to make more work for myself. I know that right here I had 0.075 moles of BF3. And then I'm going to use my balanced equation, my molar ratios. So I've got 8 BF3, and when I use all 8 BF3, I have 6 LiH. Those are my moles. And now I'm going to change my moles back to grams. We know that 1 mole of LiH has a mass of 7.9 grams. So that my moles cancel. When I do the math on this, I get 0.444 grams of LiH. This is what was used. I want to know the excess. So my excess is going to be 5 grams minus 0.444, which is going to be equal to 4.56 grams of LiH in excess. That is a limiting reagent problem. I'm just going to do one more. And there's examples of these in your textbook as well. In this one, we have equal weights of zinc. We have 5 grams of zinc, and we have 5 grams of I2. And they are mixed together to form ZnI2. So I've got Zn solid plus I2 solid yields ZnI2 solid. And that's already balanced. They've given me the atomic weight of Zn, which is equal to 65.4 AMUs, and they gave me the molecular weight of I2, which is 253.8 AMUs. So I have to determine my limiting reagent. The first way I do that is change my grams to moles. I've got 5 grams of zinc. I've got 5 grams of I2. We know that 1 mole is equal to 65.4 here, and 1 mole here is equal to 253.8. This gives me 0.0764, and this moles, and this gives me 0.0197 moles. So they both combined at a 1-to-1 ratio, so I don't have to go any further. This is present in the least, so this is my limiting reagent. So after the reaction, there will be 0 grams of I2 left. I need to figure out, if I use all of this, 0.0197 moles of I2, how much zinc will be used. Well, it's a 1-to-1 ratio. I've got 1 I2 and I've got 1 Zn. And we know that 1 mole of Zn has a mass of 65.4 grams. So Zn cancel, I2 cancel, and I get 1.29 grams of Zn when I use all of my I2. So to find out the excess, 5 minus 1.29 is going to be equal to 3.71 grams of Zn in excess. All right. Hopefully that clarifies things a little bit. If you have any problems, please message me through Schoology or Remind. Have a nice evening.